Every single particle in existence is secretly connected. From the starlight crossing the void to the very atoms in your hands, an invisible cosmic fabric binds them all. This is not a fantasy. It is the startling frontier of modern physics, a mystery we call the hidden architecture beneath quantum reality. By the end of this exploration, you will see the universe not as a collection of separate things, but as a single, unified whole. We will venture into a realm where space and time are not what they seem, and where the very notion of an isolated self begins to dissolve. How does a change in one particle instantly affect its partner, no matter the distance? What if our three-dimensional world is just a holographic projection from a two-dimensional surface? This journey will challenge everything you assume about reality itself. What does it feel like to be a thread in this cosmic tapestry? That first cosmic stitch created the entire fabric of our reality. The universe at its birth was not a random fireball, but the activation of a primordial loom, beginning to weave a pattern of unimaginable complexity. This is the concept of quantum weaving, the idea that a fundamental architecture exists beneath everything. This framework is not made of matter or energy as we know them, but of something even more basic. It is a structure that predates space and time themselves, a hidden geometry from which the cosmos is knit together. This is not a new idea. Ancient Eastern philosophies have long spoken of an indivisible wholeness, a universe where all things are interdependent threads in a single cloth. In modern science, a similar vision emerges from the work of physicist John Wheeler. He proposed the it-from-bit hypothesis, a radical notion that every particle and every force field, every it in the physical world, ultimately derives from information, from binary yes or no answers, the bits. This suggests the solid world around us is a manifestation of a deeper, information-rich reality. Theoretical physicists call this substrate the quantum foam or pre-geometric space. Think of the vacuum of space not as true emptiness, but as a seething, dynamic lattice. At the tiniest conceivable scales, this fabric is a turbulent froth where space and time lose their smooth continuity, bubbling with potential. From this energetic, information-dense framework, the particles that build our world and the forces that guide them continuously emerge. So how does this invisible loom actually operate to create the stable, predictable reality we experience every day? To answer that, we must confront the quantum realm's most bewildering and famous behavior. This spooky action at a distance reveals the first crack in our classical worldview. Einstein famously rejected the idea, calling it spooky because it seemed to suggest information could travel faster than light, breaking his theory of relativity. He, along with colleagues Podolsky and Rosen, formulated the EPR paradox as a thought experiment meant to prove quantum mechanics was incomplete. They argued that if you had two entangled particles and separated them by a vast distance, measuring one would instantly force the other into a corresponding state. For Einstein, this meant there must be some hidden variables, some unknown properties set at the moment of their creation that determined their fate, preserving local reality. For decades, this was a philosophical debate. Then, physicist John Stuart Bell found a way to test it. Bell's theorem provided a mathematical framework for an experiment that could distinguish between Einstein's local hidden variables and the spooky, non-local connection of quantum theory. When the experiments were finally conducted, the results were unequivocal. The quantum world won. Entanglement is real. Measuring one particle does indeed instantly influence its partner, no matter if they are a millimeter or a galaxy apart. This connection is not transmitted through space, it transcends it. It operates in a realm beyond our conventional understanding of location, a phenomenon we call non-locality. Physicist David Bohm offered a profound way to visualize this. He suggested reality has two orders. The explicate order is the unfolded world we see and touch, where things appear separate and distinct. But beneath it lies the implicate order, an enfolded, deeper level of reality where all things are united and separation is merely an illusion. In this view, entangled particles are not two things sending signals. They are essentially two aspects of a single, deeper entity, momentarily unfolded into what looks like separate locations. So how does this entanglement actually work at the level of the particles themselves? Think of it not as a force, but as a shared identity. When particles become entangled, they lose their individual quantum states. Instead, they are described by a single, unified quantum state. It is as if you had a pair of magical dice that always land on opposite faces. You take one die to the edge of the observable universe and roll it, getting a 3. At that exact instant, you know the die back on Earth has shown a 4. The dice did not communicate, they were always a single linked system. This is the cosmic glue, the fundamental stitch in the fabric of reality. It suggests that the particles making up your body, the light from distant stars, and the air you breathe are not isolated islands. They are intrinsically linked nodes in a vast, unbroken web of connection. A network so fundamental it challenges our deepest assumptions about what it means to be an individual object in a local region of space. If every particle is connected in this hidden architecture, what does that imply for the very nature of the space that seems to separate us? This cosmic glue of entanglement forces us to ask a startling question. What if the space we inhabit is itself an illusion, a magnificent projection from a far simpler reality? This brings us to the second principle, the holographic principle, a concept that redefines the very nature of the hidden architecture. The idea emerged not from science fiction, but from one of the most extreme environments in the cosmos, a black hole. Physicists studying black hole thermodynamics, like Jacob Bekenstein and Stephen Hawking, discovered something deeply puzzling. They found that the maximum amount of information, the entropy, a black hole can contain is not proportional to its volume, as you might expect for a three-dimensional object. Instead, it is proportional to the surface area of its event horizon, its two-dimensional boundary. This was a profound clue. It suggested that all the information needed to describe everything within a black hole, every star, every planet, every atom that fell in, could be perfectly encoded on its two-dimensional surface. Think of it like a cosmic DVD. The disk itself is flat, just 2 dimensions, but it contains all the data necessary to project a complete, immersive, 3-dimensional movie. The physicists Gerard T. Hooft and Leonard Susskind took this incredible insight and ran with it. They proposed that this might not just be a strange property of black holes, but a fundamental law of the universe. The holographic principle suggests that our entire 3-dimensional universe, with all its galaxies, planets, and people, is a holographic projection from a vast, complex, 2-dimensional surface at the cosmic boundary. In this view, you, me, everything we see and touch are like holograms. We have the convincing appearance of 3 solid dimensions, but our true source code resides on a distant, flat surface we can never see. This radically redefines the hidden architecture we have been exploring. It is no longer a structure within space, like a loom weaving threads inside a room. Instead, the architecture is the source code on the boundary. The solid world around us is the projected image, the output of that code. This has a staggering implication for the fundamental building blocks of reality. It means the universe has far fewer true degrees of freedom than we ever imagined. In a 3-dimensional world, the number of ways things can be arranged seems limitless. But if that world is just a projection from a 2-dimensional surface, then the true, fundamental information content of the cosmos is vastly smaller. Our rich, complex reality is an emergent phenomenon, an incredibly detailed illusion generated from a much simpler, 2-dimensional data set. So the chair you are sitting on feels solid, but its ultimate reality is a pattern of information stored on the edge of the cosmos. This leads us to a single, inescapable question. If our reality is a projection, what is the nature of the projector? So if our reality is a projection, what is the nature of the projector? The answer might be that the cosmos is not just a place, but a process, a vast and ongoing computation. This leads us to a radical idea, one that shifts our search for the hidden architecture from substance to software. What if the most fundamental building block of everything is not matter or energy, but information itself? This was the visionary proposal of physicist John Archibald Wheeler, who called it his it-from-bit hypothesis. He suggested that every particle, every field force, every occurrence in the physical world has at its bottom a very deep foundation, an immaterial source, a vast number of binary yes or no answers, the bits. In this view, the solidity of a rock, the warmth of sunlight, the very fabric of space, all emerge from an underlying sea of information. Think of the universe not as a giant collection of things, but as a cosmic computer. It is continuously processing these bits, and the output of that computation is the reality we perceive. The atoms in your body are not just tiny billiard balls. They are dynamic patterns of data being constantly updated. But what kind of bits could possibly build our fuzzy, probabilistic quantum world? They are not the simple zeros and ones of a classical computer. They are quantum bits or qubits. A classical bit is like a regular light switch, either definitively on or off. A qubit, however, is like a dimmer switch that can be in a superposition of both on and off at the same time. It exists in a cloud of potential, a blend of all possible states until it is observed, at which point it settles into a single, definite answer. This inherent uncertainty is not a flaw. It is the very feature that allows for the richness and complexity of our universe. It is the raw data of existence, a tapestry woven from probabilities rather than certainties. Modern physicists like Seth Lloyd have expanded on this, describing the universe explicitly as a quantum computer. In this model, every interaction, from two electrons repelling each other to a star collapsing into a black hole, is a form of quantum information processing. The particles we once thought of as solid, fundamental things are transformed into something far more fluid. They become nodes in a cosmic network, temporary manifestations of information exchange. This perspective completely reframes our search for the hidden architecture. That architecture is no longer a physical loom or a projector screen. It is the universe's operating system. And the laws of physics, from gravity to electromagnetism, are not arbitrary rules etched into the cosmos. They are the algorithms that this cosmic computer is running, the consistent, predictable software that translates the chaotic dance of qubits into the stable, classical world we navigate every day. This is a true paradigm shift. It forces us to ask, if reality is fundamentally informational, then what are we, the observers within it? What does it mean for our own consciousness to be part of this eternal calculation? This instantaneous connection across cosmic voids forces us to confront a world where distance is an illusion. The principle of non-locality states that two entangled particles can influence each other immediately, whether they are a centimeter apart or separated by billions of light years. The space between them, vast as it may seem, becomes irrelevant. It is as if the entire universe is a single, indivisible point. For decades, this was a theoretical ghost, until a series of brilliant experiments gave it substance. Physicist Alain Aspect and his team designed a test that would settle the debate between Einstein and the quantum world once and for all. They created pairs of entangled photons and sent them flying in opposite directions. At the moment of measurement, when the polarization of one photon was determined, its partner, no matter how far away, instantly assumed the corresponding state. The results were clear and repeatable. There was no hidden signal, no secret communication. The connection was simply there, a fundamental feature of reality itself. This is not a faster-than-light signal, which would still have to travel through space, taking time to cross the void. Non-locality is something far more profound. It suggests that the particles are not truly separate entities sending messages, but are expressions of a single underlying reality where separation does not exist. As the philosopher of science Bernard d'Espagnat argued, this points to a veiled reality, a deeper whole that lies beyond our direct perception. The world we see with our eyes and measure with our instruments is just a manifestation, a shadow of this unified, non-local foundation. Think of it like a vast, calm ocean. On the surface, we see individual waves, each with its own location and identity. They appear separate, rising and falling at different points. But beneath the surface, they are all connected, all part of the same body of water. A disturbance in one area can be felt everywhere, not because a ripple travels, but because it is all one substance. In this ocean of reality, the concepts of here and there lose their absolute meaning. The hidden architecture, therefore, cannot be a structure within space. It must be a logical network, a web of relationships where location is a secondary quality, not a primary one. Your hand and a star in a distant galaxy are, at this fundamental level, neighbors in a field of pure connection, a concept that leads us directly to the geometry of that field itself. The smooth, continuous space we take for granted may be the ultimate illusion. Just as a digital photograph appears seamless from a distance, reality itself might be pixelated when examined at the smallest possible scale. This leads us to a profound frontier, the geometry of spacetime. Is it an infinitely divisible smooth sheet, or is it fundamentally grainy, a fabric woven from minuscule, indivisible threads? The answer points directly to the literal, physical structure of the hidden architecture we have been exploring. At the unimaginably tiny Planck scale, a distance so small that 1 trillion of these units could fit across a single atom, our classical notions of space and time are predicted to break down. Here, the smooth continuum of Einstein's relativity is thought to dissolve into a seething, dynamic foam. This is not just empty speculation. Theories like loop quantum gravity, championed by physicists like Carlo Rovelli, offer a concrete picture. They propose that space itself is not a backdrop, but a dynamic fabric woven from finite, one-dimensional loops. Think of it as a cosmic chainmail vest. From a distance, the armor looks like a solid, continuous surface, but up close, you see it is composed of countless interlinked rings. In loop quantum gravity, these fundamental loops are the pixels of space. They connect with one another, forming an evolving network known as a spin network. These are not loops in space, they are space. Their connections and interactions define the very geometry of the universe, creating volume and area in discrete, quantized chunks. There is no such thing as a volume smaller than a single elementary loop, just as you cannot have half a pixel on your screen. This granularity is a direct, literal manifestation of the hidden architecture, the underlying latticework from which everything emerges. If this is true, then the continuous reality we experience, the smooth arc of a thrown ball, the unbroken flow of time, is an emergent property. It is a magnificent approximation, like the smooth motion in a movie that is actually a rapid succession of still frames. Our senses and even our largest instruments are simply not fine-tuned enough to perceive the fundamental flicker of this cosmic pixelation. This raises staggering questions about the most basic aspects of existence. What does it mean for something to move? If space is quantized, then motion cannot be an infinitely smooth glide. It must be a series of tiny, discrete jumps, like a cartoon character moving from one cell to the next. The very flow of time might also be granular, a sequence of fundamental moments ticking forward like the seconds on a cosmic clock. We are left with a universe that is both digital and analog, a seamless projection born from a discrete code, a continuous experience built upon a foundation of ultimate graininess. This so-called empty space is not empty at all. The quantum vacuum is a seething, dynamic sea, a vibrant substrate that defies our classical notion of nothingness. According to quantum field theory, the universe is not primarily filled with particles, but with fields. An electron field, a quark field, a Higgs field. Every fundamental entity is a field that stretches across all of space. What we perceive as a particle, like an electron, is merely a localized excitation, a tiny ripple or a vibration in its corresponding electron field. The vacuum is the lowest possible energy state of these fields, but it is far from tranquil. Imagine a perfectly calm ocean on a windless day. From a distance, it appears flat and still. But if you could look at the molecular level, you would see a chaotic dance of water molecules constantly jostling and vibrating. The quantum vacuum is like that, a frenzy of activity at the smallest scales. This activity manifests as virtual particles. Pairs of particles and their antiparticles spontaneously blink into and out of existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and returning the energy. This is not a violation of physics, but a direct consequence of the Heisenberg uncertainty principle, which allows for such energy fluctuations. But how can we know this is real and not just a mathematical trick? We can see its effects. One of the most beautiful demonstrations is the Casimir effect. Picture two perfectly smooth, uncharged metal plates placed incredibly close together in a vacuum, parallel to each other. In the empty space outside the plates, a whole spectrum of virtual particles can pop into existence, including those with longer wavelengths. In the narrow gap between the plates, however, only virtual particles with specific wavelengths that fit neatly between the plates can appear. This creates a pressure imbalance, with more virtual particle activity pushing on the plates from the outside than from the inside. The plates are gently, but measurably, forced together. It is a tangible, physical force born from the activity of nothingness. This proves the quantum vacuum is not a passive stage upon which particles perform. It is an active participant, the very ground state of the universe. This dynamic sea is the canvas upon which the hidden architecture is painted. Its constant fluctuations and virtual particle pairs represent the most fundamental level of reality we can currently conceive. A deep, foundational layer that continuously interacts with and influences every single particle we observe. The solidity of the matter around you is a stable pattern emerging from this relentless, energetic dance. This strange shift from wave to particle is not just a quirk of the laboratory. It lies at the heart of a question that has haunted physicists for a century. Does the universe only become definite, only become real when we look at it? This is the profound puzzle of the observer effect. The classic double-slit experiment reveals this mystery in its purest form. When you fire tiny particles like electrons at a barrier with two slits, they do not simply pass through one hole or the other like little bullets. If no one is watching, they behave as waves. Each electron passes through both slits at once, creating an interference pattern of ripples on the detection screen behind, a telltale signature of wave behavior. Yet the moment you place a measuring device to determine which slit any given electron goes through, the behavior changes instantly. The interference pattern vanishes. The electrons suddenly act like discrete particles, each going through a single slit and piling up in two simple bands on the screen. The very act of asking which path the electron takes forces it to pick a single, concrete reality. This is the core of the famous Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg. It posits that before measurement, particles do not have definite properties. They exist in a cloud of potential, a superposition of all possible states, described only by a probability wave. The active observation of measurement is what collapses this wave function, forcing a single, definite outcome to snap into existence. In this view, reality at its most fundamental level is inherently probabilistic, a set of possibilities that only crystallize into actual events when observed. But what or who counts as an observer? Is it a machine, a camera, a human eye? This leads to a deeply philosophical rift. Some physicists, like Eugene Wigner, argue that consciousness itself must be the ultimate trigger. Wigner proposed a famous thought experiment, suggesting that only a conscious mind could finally collapse the wave function. He speculated that the mind may be the fundamental agency that translates possibility into actuality, placing our awareness at the very center of the cosmic process. This is a staggering proposition. It suggests that consciousness is not a passive witness but an active participant in manifesting reality from the hidden architecture. Yet this idea is fiercely contested. The many worlds interpretation proposed by Hugh Everett offers a dramatic alternative. It suggests the wave function never collapses at all. Instead, every possible outcome of every quantum event actually occurs. At the moment of measurement, the universe literally splits into multiple branches. In one world, you see the electron go through the left slit. In another, nearly identical world, a version of you sees it go through the right slit. There is no special role for consciousness. Every possibility is realized in its own separate, non-communicating reality. This interpretation preserves the pure mathematics of quantum mechanics, but at the cost of an infinite, ever-branching multiverse. So where does this leave us? Is our awareness the mysterious ingredient that solidifies the quantum fog? Or are we merely one thread in an endless tapestry of parallel existences? The answer remains one of the greatest unsolved mysteries in science, a question that forces physics and philosophy to collide. It asks us to consider whether our own perception is the final stitch that completes the cosmic tapestry, weaving possibility into the world we call home. The universe's hidden architecture may be governed by a principle of profound elegance, symmetry. These are not just visual balances, but the fundamental mathematical rules from which all of physical reality is woven. At the heart of our most successful theory of particles, the Standard Model, lies a specific type of symmetry called gauge symmetry. This is a deep and powerful concept, a kind of internal flexibility that the laws of physics must possess. Imagine a field stretching across all of space, like an infinite, invisible canvas. Gauge symmetry states that the laws describing this field must remain unchanged. They must be invariant, even if we make certain local adjustments to it at every point in space. It sounds like an abstract mathematical demand, but the universe takes this requirement with utmost seriousness. In fact, to enforce this local symmetry, to keep the laws consistent despite our tinkering, a force must emerge. The electromagnetic force is precisely such a force. It is the necessary consequence of demanding a particular local symmetry for the electron field. The photon, the particle of light, is the physical manifestation of that requirement, the messenger that ensures the symmetry is never broken. This elegant pattern repeats. The strong nuclear force that binds quarks together inside protons and neutrons arises from a more complex, but equally fundamental, local symmetry. These forces are not arbitrary powers added to the universe. They are the inevitable outcomes of the cosmos obeying these deep, symmetrical rules. The dream of physics is to find a single, overarching symmetry that could describe all forces as different facets of one primordial power. This is the quest for a grand unified theory, or GUT. Such a theory would reveal that at extremely high energies, like those just after the Big Bang, the electromagnetic force, the weak nuclear force, and the strong nuclear force were not separate at all. They were one unified force, described by a magnificent single symmetry. As the universe expanded and cooled, this perfect symmetry broke. like a single crystal shattering into distinct pieces, giving us the distinct forces we observe today. The ultimate goal goes even further, a theory of everything that would incorporate the fourth force, gravity, into this unified picture. This would describe the hidden architecture in its most pristine, mathematical state, a reality where one simple, symmetrical principle generates the entirety of existence, from the whirl of galaxies to the bonds in a molecule. Our complex universe of diverse particles and forces, then, is the frozen, fragmented reflection of a deeper, perfectly unified state of being, a cosmic code written in the language of symmetry. The universe we see, with its glittering galaxies and swirling nebulae, is only a tiny fraction of what is actually there. The overwhelming majority of the cosmos is made of stuff we cannot see, two profound enigmas known as dark matter and dark energy. Together, they dominate the universe's composition and its ultimate fate, pointing directly to the hidden architecture we have been exploring. Think of dark matter like the wake of an unseen boat. You can see the powerful, swirling water churned up behind it. You can measure its effect on the surrounding sea, but the vessel itself remains completely invisible. This is precisely how we detected dark matter. Astronomers observed that galaxies were spinning so fast that the gravity from their visible stars and gas was utterly insufficient to hold them together. They should have flown apart long ago. The only explanation was that each galaxy is embedded within a massive, invisible halo of something that exerts a tremendous gravitational pull, a something we call dark matter. This unseen substance binds the cosmos, a cosmic glue operating on the grandest scales. What could this mysterious substance be? One leading idea is that dark matter is composed of entirely new, undiscovered particles that interact with the hidden network in a profoundly different way. Unlike the particles we know, which are constantly exchanging photons and other force carriers, these dark matter particles might interact only through gravity and perhaps one other extremely weak force. They would be ghostly inhabitants of the same reality, woven into the same cosmic tapestry, but nearly oblivious to the vibrant electromagnetic interactions that make up our world of light and matter. They are there, part of the architecture, but they are like silent threads in the weave, felt only by their gravitational tug. Alternatively, this mystery might be telling us that our understanding of gravity itself is incomplete. Perhaps on the vast scales of galaxies, gravity behaves differently than Einstein's theory predicts, and no invisible matter is required. This idea, known as modified Newtonian dynamics, or MIND, suggests the architecture has a different set of rules for the cosmic dance than we once thought. Then there is the even more baffling mystery of dark energy. In the late 1990s, astronomers made a shocking discovery. They found that not only is the universe expanding, but this expansion is accelerating. Something is actively pushing galaxies apart with ever-increasing force. This something is dark energy. The most straightforward explanation is that dark energy is an intrinsic property of the vacuum of space itself, what Einstein once called the cosmological constant. It is a constant, relentless energy density woven into the very fabric of the hidden architecture. As the universe expands and more space is created, more of this repulsive energy appears, causing the acceleration to grow. If the hidden architecture is an informational framework or a quantum field, then dark energy could be a fundamental pressure encoded within its very structure, a built-in tendency for the cosmic fabric to stretch itself. These twin enigmas present us with a humbling reality. The atoms that form everything we can see, from the tallest mountain to the most distant star, account for less than 5% of the universe. The remaining 95% is this dark, unknown realm. This suggests that the visible universe is just a shimmering pattern on the surface of a much deeper, mostly invisible cosmic structure. The true nature of reality, its mass and its motion, is dictated by forces and substances whose essence remains hidden from our view. yet whose signature is written into the gravitational skeleton of the cosmos and the accelerating fate of all we see. The architecture is mostly dark, its blueprint written in a language of gravity and vacuum energy we are only beginning to decipher. A single starling has no concept of the vast, swirling shape it helps to create. It follows only a few simple rules, staying close to its neighbors, matching their speed, and avoiding collisions. Yet from this local choreography, a murmuration emerges, a breathtaking, fluid intelligence that seems to have a mind of its own. The flock is a property of the collective, something that does not exist at the level of any individual bird. This is the magic of emergence, the sixth principle, where the whole becomes undeniably greater than the sum of its parts. And this is not just a beautiful natural phenomenon. It is a fundamental law of organization that appears to govern every layer of reality, all the way down to the hidden architecture itself. Consider the solidity of the floor beneath your feet. At our human scale, it is hard, continuous, and impenetrable, but descend to the atomic level, and that solidity vanishes. You find a realm of overwhelming empty space, with tiny electrons whizzing around nuclei at vast distances. The solidity you experience is not a property of individual atoms, it is an emergent property. It arises from the collective electromagnetic interactions of countless atoms, creating a force field so powerful, it feels utterly solid to your touch. Temperature is another powerful example. A single atom cannot be hot or cold. It only has kinetic energy, a speed of motion. But take a vast collection of those atoms, and the average of all that jostling and vibration emerges as the property we call temperature. These are not illusions, they are real phenomena that only exist at a specific level of complexity. Now apply this profound idea to the hidden architecture of quantum reality. What if the particles we think of as fundamental are themselves emergent? What if they are not tiny billiard balls, but stable patterns, like persistent whirlpools in a flowing river of something more basic? In this view, an electron is not a thing but a behavior, an excitation that emerges from the ongoing dynamics of an underlying quantum field. And what of space and time, the very stage upon which everything plays out? The principle of emergence suggests they, too, might not be fundamental. The smooth, continuous spacetime of our daily experience could be a large-scale approximation, an emergent property arising from the collective relationships within a deeper network. Think of the three-dimensional world generated by a two-dimensional hologram, or the smooth motion of a movie emerging from a sequence of discrete frames. Our reality may be a stratified cosmos with multiple layers, each with its own emergent laws and properties. The chemistry of molecules emerges from the physics of atoms. The biology of life emerges from the chemistry of complex molecules. And our conscious awareness may itself be the most stunning emergent phenomenon of all, arising from the intricate network of neurons in our brains. This leads to a staggering conclusion about the hidden architecture. It might not be made of stuff at all, not in any way we can conceive. Its fundamental nature could be pure relationship, a vast web of dynamic processes and logical interactions. The solidity, the forces, and even the flow of time in our world would then be the grandest emergent properties of all, a cosmic performance generated by a deeper, simpler code. So where did these layers of reality, this entire cascade of emergence, originally come from? An ice cube melts in a warm room, but you never see the puddle of water spontaneously refreeze into a perfect cube. This simple, everyday observation points to one of the deepest mysteries in all of physics. Why does time have a preferred direction? Why do we remember the past but not the future? This irreversible flow, this arrow of time, is governed by a fundamental cosmic rule known as the second law of thermodynamics. The law states that in any closed system, a quantity called entropy, which is a measure of disorder or randomness, always increases or at best stays the same. It never spontaneously decreases. A shattered glass does not reassemble. A dispersed perfume cloud does not gather back into the bottle. And the universe as a whole is marching from a state of lower entropy in the past toward a state of maximum entropy in the future. An eventual cosmic heat death where all energy is evenly distributed and no more work can be done. But this presents a profound puzzle. If the universe is inevitably headed toward maximum disorder, how did it start in a state of such incredibly low entropy to begin with? The Big Bang appears to have been an event of exquisite, improbable order. This is known as the past hypothesis, the puzzle of our special cosmic beginning. One radical and deeply unsettling proposal to avoid this special beginning is the Boltzmann brane paradox. The physicist Ludwig Boltzmann once speculated that if you wait long enough in a high-entropy, chaotic universe, random fluctuations will eventually create any configuration, no matter how ordered. In a vast, almost dead cosmos, it is statistically more likely for a single, fully formed brain with false memories of a past to spontaneously fluctuate into existence than for an entire, ordered universe like ours to do so. So, are you a Boltzmann brain? A momentary flicker of order in an eternal sea of chaos, with your entire life and memory just an illusion? Most physicists reject this idea, but it highlights the sheer strangeness of our low-entropy origin. The solution to this puzzle may lie in the very nature of time itself. What if time is not a fundamental component of the hidden architecture? Groundbreaking work by physicists like John Wheeler and Bryce DeWitt suggests exactly that. Their Wheeler-DeWitt equation, an attempt to merge general relativity with quantum mechanics, famously describes a static universe, a timeless block where the entire history of existence is just there. In this view, the flow of time is an emergent property, a compelling illusion generated by the changing relationships and correlations within the cosmic network. Think of a movie. The film strip itself contains every frame, past, present, and future, existing all at once. But when projected, the sequential illumination of each frame, the correlation between one image and the next, creates the powerful, irresistible illusion of flow and change. In our universe, time's arrow may emerge from how information is processed and stored within the hidden architecture. Every interaction, every quantum measurement, creates new correlations and increases the total information content of the network. This continuous updating of relational information is what we perceive as the forward march of time. The increase of entropy is simply the universe's way of keeping a permanent, irreversible record of these events. Once a correlation is made, it cannot be unmade without violating the logical consistency of the network. This reframes time from a background stage upon which events play out into a dynamic feature generated by the architecture's state. Our macroscopic experience of a past, present, and future, of cause and effect, is a direct consequence of how the microscopic quantum world processes information. The arrow of time is the signature of the cosmic computer running its software, an emergent story written in the accumulating connections of the hidden network. The shape of reality itself might be far stranger than a simple, infinite void. To understand this, we must venture into the abstract world of topology, the mathematical study of properties that survive stretching, twisting, and squeezing. A topologist sees a coffee mug and a donut as identical because each has exactly one hole, a handle you can hold or a tunnel through the pastry. The specific shape does not matter, only the fundamental connectivity. What if the entire cosmic network, the hidden architecture of everything, possesses a non-trivial topology? Our universe might not be a flat, endless plane. It could be folded into a vast, cosmic donut, a shape known as a torus. In such a universe, if you could travel in a perfectly straight line for long enough, you would not journey forever into nothingness. You would eventually return to your starting point from the opposite direction, like an ant walking on the surface of a bagel. This is not just a mathematical curiosity. It leaves a potential fingerprint on the oldest light in the cosmos, the cosmic microwave background. If space has a complex, multi-connected topology, astronomers might find repeating patterns in this primordial glow, like matching circles on the sky, evidence that the fabric of reality wraps around on itself. This topological perspective also breathes life into one of science fiction's most enduring concepts, the wormhole. Known in physics as an Einstein-Rosen bridge, a wormhole is essentially a topological shortcut, a tunnel connecting two distant points in spacetime. Think of the cosmic network not as a flat sheet of paper, but as a folded piece of paper where two points can be brought into direct contact. A wormhole is the stable stitch that holds those 2 points together, a literal manifestation of the network's hidden connectivity. From this vantage point, the hidden architecture is not a chaotic, random tangle of threads. It possesses a specific, elegant topological structure, a geometric signature that dictates all possible connections and pathways between every point in reality. The laws of physics we observe could be a direct consequence of this ultimate shape, a cosmic code written not just in equations, but in the very geometry of the whole. If the architecture has a specific shape, what does that imply for the building blocks it is made from? The clash between our two greatest theories of reality is a silent war fought at the boundaries of the cosmos. In the realm of the atom, quantum mechanics paints a universe of probability and chance, where particles flicker in and out of existence. Out in the cosmos, Einstein's general relativity describes a universe of smooth, curving geometry, where gravity is the elegant warping of spacetime itself. Both are spectacularly successful in their own domains, but when forced to meet, their mathematical languages become mutually unintelligible. This conflict becomes a crisis in the most extreme environments, like the singularity at the heart of a black hole or the very first moment of the Big Bang. In these places, immense mass must be squeezed into a vanishingly small quantum volume, and our equations simply explode into nonsense. To resolve this, we need a theory of quantum gravity, a single framework that can describe the hidden architecture when it is bent to its absolute limit. Two towering contenders have emerged from this struggle, each offering a radically different vision of that fundamental structure. String theory proposes that the ultimate building blocks are not point-like particles, but unimaginably tiny, vibrating loops of energy. An electron is a string vibrating one way, a quark is that same string vibrating another way, and the photon is yet another vibration. In this symphony of strings, even gravity emerges from a specific vibrational pattern, the graviton. To make the math work, string theory requires more than the three spatial dimensions we experience, suggesting the architecture is woven within several extra, curled-up dimensions. Loop quantum gravity, the other great contender, takes a different path. It does not add new dimensions but fundamentally rethinks the nature of space itself. It proposes that space is not a smooth continuum, but is woven from a fabric of finite, interwoven loops. These loops form a dynamic, granular network, a spin foam, where volume and area come in discrete, indivisible units. There is no such thing as a space smaller than one of these elementary loops, just as you cannot have half a pixel on a screen. In this view, the architecture is not made of strings vibrating within space. It is the literal quantum structure of space and time itself. A successful theory of quantum gravity, whether it follows one of these paths or one yet unknown, would answer the most profound question of all: what are the atoms of space-time? We know matter is made of atoms. Energy comes in quanta. So it seems inevitable that the fabric of reality itself must also be granular at the tiniest scale. Discovering this fundamental grain, this ultimate pixel of the cosmos, would reveal the true nature of the network that connects every particle. It would show us the loom upon which the entire cosmic tapestry is woven, bringing us face to face with the raw code of existence. The ultimate loom weaving our reality might not be a force of nature at all, but a line of code running on an unfathomable computer. This is the simulation hypothesis, a modern philosophical proposition that reframes our entire cosmic mystery. Think of the universe not as a spontaneous creation, but as a simulation, a hyper-advanced reality engine built by a civilization so technologically mature that their computing power could model every star, every atom, and every conscious mind within it. In this scenario, the hidden architecture we have been exploring is not a fundamental property of an independent cosmos. It is the literal source code of the simulation, the programmed rule set that defines our existence. The laws of physics become the software's algorithms, the elegant mathematical symmetries are its optimized functions, and the quantum foam is the resolution of the render, the smallest pixel this cosmic computer can process. The strange, discrete nature of quantum mechanics, where properties are quantized and exist in definite states only upon observation, fits perfectly with this idea. It mirrors how a video game engine works, only calculating the precise details of a scene when a player is there to look at it, saving processing power by leaving distant mountains as low-resolution probabilities. The holographic principle deepens this analogy. The notion that all the information describing our three-dimensional world is stored on a two-dimensional boundary is exactly how complex simulations often function, with the rich, interactive world being projected from a simpler, underlying data structure. If this is true, then the programmers of our reality exist entirely outside our spacetime continuum. They are not gods in a traditional sense, but perhaps beings of a base reality, engineers who built our universe as an experiment, a form of entertainment, or an ancestral archive. This forces a radical reinterpretation of the cosmic network. It is not a natural phenomenon emerging from nothing, but an intentionally engineered construct, designed with a specific purpose we cannot possibly discern from within the program. The profound connection of entanglement is then not a mysterious cosmic glue, but a clever programming shortcut, a linked variable ensuring two separated objects remain correlated without constant updates. What does this mean for our own consciousness? Are our thoughts and feelings merely sophisticated outputs of the simulation, complex algorithms experiencing themselves? Or is consciousness the one thing that cannot be simulated, a spark from the base reality that has been uploaded into this digital cosmos? While this idea is highly speculative and currently untestable, it compels us to confront the nature of existence itself. It suggests that the search for the hidden architecture is ultimately a search for the programmer's signature, a glimpse into the logic of a reality whose true dimensions and nature may forever lie beyond our coded grasp. Our universe might be a single bubble in a cosmic sea of froth. This is the inflationary multiverse, a direct extension of the theory of cosmic inflation. The idea is that the same primordial field, the inflaton that drove our universe's explosive initial expansion, continues to ripple and fluctuate in a much vaster, background cosmos. In some regions, this field drops to a lower energy state, and that local drop triggers a new Big Bang, inflating a new bubble universe. Each of these bubbles could have its own unique properties, forever disconnected from our own space-time continuum. They are not far away in our space. They are separate realities altogether, each with its own story. But the variety does not end there. String theory adds another layer to this cosmic library. Its mathematical framework suggests not one, but a staggering number of possible stable configurations for the extra dimensions it requires, perhaps 10 to the 500 different possibilities. This is the string theory landscape. Each point in this landscape represents a different vacuum state, a unique set of physical laws and constants. In one, gravity might be 1 billion times stronger, making our universe impossible. In another, the nuclear forces might be too weak to form atoms, Our universe, with its specific, life-permitting constants, is just one fortunate page in an encyclopedia of almost infinite alternatives. This leads to a vision of reality where the hidden architecture we have been exploring is not a universal blueprint, but a local building code. The quantum network connecting our particles, the holographic screen encoding our reality, might be just one instance of a pattern repeated across countless cosmic domains. But what if the connections themselves originate from beyond our familiar dimensions? This is the realm of brain-world scenarios. In M-theory, which unites different versions of string theory, our entire three-dimensional universe could be a three-dimensional membrane, or brain for short, floating within a higher dimensional space called the bulk. All the particles and forces we know, except for gravity, might be stuck to our brain like ink on a page. We cannot perceive the bulk directly, but gravity, the warping of space-time, can leak across it. In this breathtaking picture, the cosmic network is not confined to our three dimensions. The instantaneous link of quantum entanglement, that spooky connection that defies local space, might be a shadow. It could be the visible effect of particles that are deeply connected through a shortcut in a higher dimension, their interaction simply taking a path we are blind to. The true scale of the hidden architecture becomes almost incomprehensible. It is no longer just the fabric of our reality, but a multi-dimensional tapestry of which our universe is but a single, shimmering thread. A black hole is far more than a simple trap for light and matter. It may be a fundamental engine in the cosmic network, a processor that transforms reality at its most basic level. This role was thrown into sharp relief by Stephen Hawking's revolutionary discovery of Hawking radiation. He realized that black holes are not completely black. Due to quantum effects at the very edge of their event horizons, they slowly leak radiation and over eons can evaporate completely. This created a terrifying paradox. If a black hole vanishes, what happens to all the information about the stars, planets, and atoms that fell into it? According to quantum mechanics, information is never truly destroyed. It can be scrambled but never erased from the universe. Hawking's calculations suggested it was lost forever, a direct violation of a core quantum rule. This black hole information paradox meant our two most powerful theories of reality were fundamentally at odds. The resolution came from the holographic principle. The work of physicists like Leonard Susskind revealed that the information about every single thing that crosses the event horizon is not lost inside the singularity. Instead, it is perfectly encoded bit by bit on the two-dimensional surface of the event horizon itself. The black hole's surface area becomes a vast, cosmic hard drive, storing the complete description of everything within its volume. This transforms our view of a black hole from a destructive pit into the ultimate information processor. It takes the complex, three-dimensional data of infalling matter and computes a perfect two-dimensional representation, a hologram. It is constantly performing a universe-scale calculation, processing the data of existence itself. This profound link between information and geometry leads to an even more beautiful idea, the ER equals EPR conjecture. It proposes a deep unity between two concepts we thought were separate. EPR, from the Einstein-Podolsky-Rosen paradox, represents the bizarre, instantaneous connection of quantum entanglement. From Einstein and Rosen, represents wormholes, the bridges in the fabric of spacetime. The conjecture suggests they are one and the same. Those spookily connected entangled particles are not communicating faster than light. They are directly linked by a microscopic, wormhole-like structure in the hidden architecture. Every quantum connection is a tiny stitch in the fabric of spacetime, a minuscule tunnel binding the universe into a single, inseparable whole. This means the cosmic web connecting every particle is woven from an unimaginably dense tapestry of these geometric links, with black holes serving as powerful, natural nodes where information is processed. and the very threads of reality are spun. Our entire experience of reality rests on the unshakable rule that every effect is preceded by a cause. A ball moves because a foot kicked it. A fire burns because a match was struck. This chain of causality is the logical backbone of our universe, the very framework that makes science and even daily life possible. Einstein's theory of relativity gave this framework a precise geometric shape, the light cone. Picture every event in spacetime, every decision you make, as a single point. From that point, a cone extends into the future, defining the maximum region that any influence, traveling at or below the speed of light, can possibly reach. Another cone extends into the past, containing every event that could have possibly influenced you. This elegant structure ensures a strict cosmic order, preventing causes from having effects that precede them, preserving the sanctity of time's arrow. Yet the quantum world defies this classical order with its spooky connections. When we measure one entangled particle, its partner instantly responds, no matter if it lies inside or outside our past light cone. The correlation is immediate, appearing to operate outside the relativistic speed limit. This is not a signal you can use to send a message into your own past, but it is a correlation that exists without a clear, local cause in the classical sense. So which picture is true? Is the universe a neatly structured arena of causes and effects, or a deeply interconnected web where influence transcends our notions of before and after? The growing consensus is that our classical, linear causality is not a fundamental law of the cosmos, but an emergent property. It is a robust approximation that works perfectly in our everyday world, much like Newton's laws of motion work until you approach the speed of light. In the deeper, hidden architecture, the network of quantum connections may be a causal. The relationships between events might be primary, with our experience of cause and effect being a secondary, large-scale consequence. In this fundamental network, the concepts of before and after could lose their absolute meaning. The cosmic computer does not process events in a single, linear sequence. It might compute the state of the entire network as a whole, with our perception of a cause leading to an effect being just one thread in a vastly more complex tapestry of logical connection. This forces a profound re-examination of concepts we hold dear, like free will and destiny. If the future is already woven into the timeless connections of the cosmic network, does our choice have any real power? Or is our feeling of making a decision simply the way this complex computation feels from the inside? The puzzle of causality remains one of the most active and mind-bending frontiers in physics, a direct challenge to our most basic assumptions about how reality operates. These mind-bending ideas are not confined to the blackboard. They are being hunted down by colossal machines and delicate instruments, transforming cosmic philosophy into hard, empirical science. At the forefront is the Large Hadron Collider, the most powerful particle accelerator ever built. By smashing protons together at nearly the speed of light, it recreates the searing conditions of the early universe, probing for the hidden architecture's signature. Scientists are searching for supersymmetric particles, potential partners for every known particle we have. Discovering them would be a monumental step toward unifying the forces of nature. The collider could also find evidence for extraspatial dimensions, perhaps by detecting particles that momentarily vanish from our three-dimensional brain only to reappear, having traveled through a hidden dimension we cannot see. While we recreate the universe's first moments on Earth, another frontier is opening in the realm of computation. Quantum computers are not just faster calculators, they are machines that operate on the very principles of the cosmic network. By harnessing the power of qubits, superposition, and entanglement, they process information in a way that mimics the universe's own underlying mechanics. A sufficiently powerful quantum computer could simulate aspects of the hidden architecture itself, allowing us to run experiments on the fabric of reality within a controlled environment, exploring how space-time and particles might emerge from pure information. Our search extends far beyond our planet, into the faint echo of creation. The cosmic microwave background is the oldest light in the universe, a fossilized snapshot from just after the Big Bang. By mapping its minute temperature fluctuations with incredible precision, observatories like the Planck satellite look for the fingerprints of a complex cosmic topology. Are there matching circles in this ancient glow? Evidence that the universe wraps around on itself like a cosmic donut. These subtle patterns could reveal the ultimate shape of the hidden network. The same primordial light might carry the faint imprint of gravitational waves from the universe's violent birth, ripples that would tell us about the quantum nature of gravity itself. To catch these ripples directly, we are building observatories in space. The Laser Interferometer Space Antenna, or LISA, is a planned mission that will form a giant triangle of 3 spacecraft, millions of kilometers apart. They will use lasers to detect the infinitesimal stretching and squeezing of space-time caused by merging supermassive black holes and other colossal events. By listening to the gravitational waves these events produce, LISA will test general relativity in its most extreme regimes and potentially hear the vibrations of the cosmic strings or other defects that may have formed as the hidden architecture cooled and solidified after the Big Bang. These experimental frontiers are our only window into the Planck scale, the realm where the fabric of spacetime itself is thought to be granular. We cannot travel there, but we can build extensions of our senses, machines that translate the whispers of the quantum void into data we can understand. Each experiment, from the colossal to the quantum, is a different way of asking the same fundamental question, turning the page from speculation toward a tangible map of reality's source code. This breathtaking fine-tuning of the cosmos presents a puzzle that echoes back to our own existence. If the force of gravity were even a fraction stronger, the universe would have collapsed back on itself in a fiery crunch moments after the Big Bang. If it were slightly weaker, matter would have flown apart too quickly to ever coalesce into galaxies and stars. The mass of the electron, the strength of the nuclear forces, every single constant seems perfectly calibrated, as if the dials of reality were set with exquisite precision to allow for planets, chemistry, and ultimately, life. This is the enigma of the Anthropic Principle, a concept that forces us to confront why the universe appears so hospitable to observers like us. The weak Anthropic Principle offers a straightforward, almost logical answer. It states that we can only observe a universe that is compatible with our existence. In a cosmos where the constants were set at random, we inevitably find ourselves in one of the rare pockets where those constants allow for complex structures. It is a cosmic version of the survivor bias. You do not wonder why you are breathing air after falling overboard. You simply recognize that you would not be around to ponder the question if you were not. This perspective finds a powerful home in the multiverse theory. If our universe is just one bubble in an infinite froth of universes, each with its own random set of physical laws, then there is no mystery. We simply live in the one bubble where the quantum architecture, by sheer chance, produced the right parameters for stars to shine and life to emerge. The strong Anthropic Principle, however, pushes into more profound territory. It suggests the universe must, in some deep sense, have properties that allow for the development of conscious life. This is not a selection effect, but a fundamental feature of the cosmic network itself. It implies that the hidden architecture might be wired with a kind of bias, a built-in tendency toward complexity and awareness. The laws of physics are not a random draw, but the only possible laws that could lead to a self-aware cosmos. This idea straddles the delicate line between science and metaphysics, pointing toward a universe that is not merely a collection of particles, but a system with a potential for meaning. Is the fine-tuning we witness merely a fortunate accident in an infinite cosmic lottery? Or is it the signature of a deeper principle woven into the fabric of the network itself? A whisper that the architecture was always destined to look back upon itself. For centuries, we have seen ourselves as isolated spectators in a vast, mechanical cosmos. We believed the universe was a collection of separate objects, a grand clockwork where we were merely tiny, independent cogs. This classical view shaped our very sense of self, reinforcing the idea of a distinct inner world divided from an external reality. But the hidden architecture of quantum reality shatters this illusion. It reveals a cosmos where every particle in your body is fundamentally linked to the farthest star, not by invisible threads, but through a deeper unity where separation is the illusion. This shift from a universe of parts to a universe of a whole forces us to confront the most intimate questions of identity. If we are all nodes in a single, unbroken network, where do we end and the rest of the world begins? The feeling of a separate self, the I that seems to reside inside your head, may be a compelling, persistent story told by the brain, but not the ultimate truth of our existence. This perspective resonates powerfully with ancient Eastern philosophies. The Hindu tradition of Advaita Vedanta speaks of a non-dual reality, where the individual soul and the universal Brahman are one. Buddhist teachings on interdependence describe all phenomena as empty of independent existence, arising only in relation to everything else. A wave on the ocean may have a temporary, individual form, but it is never truly separate from the water it is made of. Our modern physics is now arriving at a strikingly similar conclusion, not through spiritual insight, but through the rigorous language of mathematics and experimentation. This understanding profoundly impacts our sense of free will. In a completely deterministic, clockwork universe, free will was always a puzzling ghost. But in a deeply interconnected, probabilistic quantum network, our choices might not be the commands of an isolated captain. They could be the creative expressions of the entire network itself, decisions emerging from the cosmic whole through the localized node we call ourself. Our consciousness itself may not be a private event locked inside our skull. It could be a fundamental quality of the universe, a property of the network's intricate connectivity, with our individual awareness being a focused, personal expression of a broader cosmic sentience. This is not to erase our personal experiences, but to place them in a grander context. Embracing this world, has transformative ethical consequences. If we are all expressions of a single reality, then harming another person or destroying an ecosystem is ultimately a form of self-harm. It fosters a natural ethic of compassion and responsibility, a recognition that our well-being is inextricably linked to the well-being of the whole. The hidden architecture, therefore, is far more than a physical theory. It is the foundation for a new story of who we are. A narrative that bridges the ancient chasm between scientific discovery and spiritual wisdom, inviting us to see ourselves not as solitary fragments, but as unique and irreplaceable expressions of a unified cosmos. The future of physics is no longer a search for isolated particles, but for the pattern that connects them all. We are assembling the ultimate cosmic puzzle, and the next generation of tools will let us see the picture on the box. The race is on to build particle colliders of unprecedented scale, machines that could recreate the conditions of the universe a trillionth of a second after the Big Bang. These colossal rings would probe energies where the fundamental forces of nature are predicted to merge into one, potentially revealing the unified field that is the source of the cosmic network. Beyond our planet, the James Webb Space Telescope and its successors act as time machines, peering back to the formation of the first galaxies. They are not just looking at stars, they are mapping the gravitational skeleton of the cosmos, tracing the influence of dark matter and the push of dark energy, directly observing how the hidden architecture shapes the universe on the grandest scale. Meanwhile, down on Earth, A quieter revolution is underway with quantum sensors. These exquisitely delicate devices can measure minuscule distortions in spacetime and tiny magnetic fields, hunting for the faint whispers of theoretical particles that might compose dark matter or for the subtle signatures of quantum gravity. The data from these experiments is so vast and complex that no human mind could ever sift through it. This is where artificial intelligence enters the stage. Machine learning algorithms are now essential partners, scanning the cosmic noise for patterns we would never spot, finding correlations in the data that could point the way to new physical laws. They are like digital oracles, helping us decode the universe's source code. The ultimate goal, the holy grail of this entire endeavor, is a final theory, a single, elegant set of equations that would describe the hidden architecture in its entirety. This theory of everything would show us how the holographic principle, quantum entanglement, and the granularity of spacetime are all different facets of one profound truth. It would reveal a cosmos that is not a collection of things, but a single, dynamically connected process. This is the quest that will define science for centuries, a journey to answer the most human of questions: where did we come from? By finally understanding the fabric from which we are woven. Look at your own hand for a moment. The skin, the bones, the blood vessels you see are composed of atoms that were created in the heart of ancient, long-dead stars. Every element essential for life was forged in those stellar furnaces and scattered across the galaxy by cataclysmic supernova. But the connection runs far deeper than a shared cosmic origin. The very particles that make up your body are, at this instant, entangled with partners stretching across the vastness of space. You are not merely a passive collection of stardust observing the universe from a distance. You are a localized expression of the cosmos itself, a temporary and vibrant concentration of the universal field, a ripple that has gained just enough coherence to look back upon the ocean from which it came. What does it feel like to be a node in this infinite network? That subtle sense of wonder you feel when gazing at the night sky, that profound peace in moments of deep connection with nature, or the startling clarity of a new idea. These are not just neurological events. They might be the hidden architecture whispering to you, reminders of your true, unbounded nature. The feeling of a separate self, the I that seems to reside behind your eyes, is a convincing story told by the brain. Yet the deeper reality, revealed by the quantum weave, is that there is no final boundary where you end and the rest of the universe begins. You are the cosmos experiencing itself. This realization transforms the hidden architecture from an abstract scientific concept into the most intimate truth of your existence. The mystery of connection is not a remote puzzle for physicists alone. It is the very fabric of your consciousness, the silent, humming network that binds your every thought and sensation to the whole of reality. Before we wrap up this journey, it's essential to separate the science from the science fiction that often clouds this topic. A common misunderstanding is that the hidden architecture implies a conscious creator or a divine hand. In truth, this framework is a natural, physical structure emerging from the fundamental laws of physics, not a blueprint requiring a designer. The cosmic network operates on mathematical principles, not intentional design. Another crucial clarification involves quantum entanglement. While two particles influence each other instantly across any distance, this phenomenon cannot be used to send messages faster than light. The correlation is immediate, but it is random. You cannot control the state of one particle to transmit a coded signal to its partner, which preserves the sacred rule of causality and ensures our universe remains logically consistent. Then there is the simulation hypothesis, the idea that we might be living in an advanced computational construct. This is a fascinating philosophical interpretation, a thought experiment that reframes our questions, but it is not an established scientific fact. There is currently no testable evidence to support it, and it remains a speculative proposition rather than a theory with predictive power. It is also a mistake to think these quantum and holographic principles invalidate the physics of Newton and Einstein. Classical physics is not wrong. It is brilliantly accurate within its domain, the world of human scales and speeds. The hidden architecture does not overthrow these laws. It provides their deeper, more fundamental foundation, explaining why the classical world emerges so reliably from the quantum realm. Finally, the notion that human consciousness causes the collapse of the wave function is just one interpretation among several. The Copenhagen interpretation suggests this, but other compelling views, like the many worlds interpretation, remove the observer's special role entirely. The science is still debating this core mystery. Clearing up these points is not about limiting wonder, but about grounding our awe in rigor. It ensures our exploration of the cosmos's deepest secrets is built on a foundation of clarity, preventing the spread of pseudoscience and allowing the true, staggering beauty of the hidden architecture to shine through, unobscured by myth. The journey through the quantum weave reveals a cosmos of breathtaking unity. We have navigated from the spooky link between entangled particles to the holographic screen from which our world projects, from the pixelated fabric of spacetime to the profound possibility of a cosmic computation. Each thread leads to the same stunning realization that our experience of separateness is a compelling illusion. We are not isolated spectators in a vast machine, but active participants in a single, dynamic, and unimaginably complex network, a hidden architecture connecting every particle that has ever existed. Carl Sagan's words echo this truth with poetic force. The cosmos is within us. We are made of star stuff. We are a way for the cosmos to know itself. This exploration does not end here. It is an open invitation. An invitation to keep questioning the nature of your own reality, to keep exploring the deep mysteries of existence, and to never stop marveling at the interconnected whole of which you are an inseparable part. We would love to hear your thoughts and questions in the comments below. And if you want to continue this cosmic exploration with us, please subscribe.